Day 8. Welcome back. The goals for today are to look at the central limit theorem for means and for proportions. So we're going to do both today. The big thing, and let's start with some notation reminders. First of all, this is something I actually provide you with a summary page, and you'll know I'll pop that up within the next couple days for the exam so that you have a lot of these things right at your fingertips all pulled together neatly. But some notation to remember is that if we have pi, we're looking at the probability of success in a population, okay? Mu is for the population mean and sigma is for the population standard deviation. On the other hand, p hat is for the proportion in the samples, x bar is for the sample mean, and s, small s, is for the sample standard deviation. So a lot of times I'll just say SD, but whenever we're talking about the population, we should really make sure we use population standard deviation, we should really use mu. So we're going to take a look at how the central limit theorem works, what it means. So the central limit theorem tells us, now you do not have to memorize this, remember you'll have your notes with us, but this gives us a powerful tool to be able to do some calculations more quickly and easily. When we have random samples of size n are taken from a large population, and we'll talk more about that in a moment, the distributions of the values of the sample means, so we're looking specifically at means, sample means right now, or sample averages, is calculated for the sample has a mean mu. You're like, well, mean mu, isn't that the related to the population? Yes, bear with me though. Standard deviation for that is going to be sigma over the square root of n, where the population, mu is the population mean and sigma is the population standard deviation. So that may feel really strange because you're like, well, how are we going to know these? We'll work through it. Don't worry, you will be given this information in terms of the number. So once again, you will not have to try to calculate or figure out exactly what sigma would be. The central limit theorem also tells us the overall shape of the distribution is approximately symmetric and bell-shaped, aka normal, if either the sample is large enough, typically 20 or more, or the sample appears to have come from a population that has a normal distribution. And the population is considered, we talked about earlier, large enough if its size is at least more than 10 to 20 times the sample size. So if you have a sample of 20, we'd want the population to be at least 200. Now, I'd like to take a minute and pop back, if you can pause this and grab yesterday's notes for me. So I want to go back, and this is, sorry, page 45. I want to just talk about skewed a little bit. I remember thinking about it, I'd like to spend a little more time on it. Now remember, we said with that central limit theorem, either we have to have the sample is large enough, being 20 or more, or the sample appears to come from a population that has a normal distribution. Remember, normal distribution, oops, pardon me here, is a pretty bell, right? And it helps if I actually tap that. It looks like this. I wanted to show you on this, here we have population data. This is based on means, because we were doing the average length there. And this distinctly does not, this is where the center would be. This is definitely skewed, because there's a bunch of stuff over here that are going to pull. Remember, if we have some bigger numbers, is that going to pull if you average some, let's say you had a 0, 0, 0, and 100. Well, really, you're closer to 0, but you average in that 100, and it really pulls up what the overall average is. All right, so that's when we say something is skewed. We skew towards. This is skewed right. Wherever the oddness is, that's what we skew towards. So that's just something I want you to keep in mind as we talk through these. and we'll hit that again later. The other thing is I made a notation mistake, and I apologize. On page 46, I should not have used X bar. I should have just said, it said, what is the mean and standard deviation for this graph? I should have just written mean because X bars were taking each of the averages. So I apologize for that. So going back, the mean for the distribution of sample means from the previous class, and I'm just going to write that down for us. So it may be helpful to have your day 7 notes with you. This is on page 46, but we found the sample means, the mean of the distribution of sample means, excuse me, was a 4.319. Is that equal to or very close to mu equals 4.295? Sure, that looks pretty close. Yeah, I'd say those are pretty close. Now the standard deviation for this sample means was also given to us, and that's 0.956. Is that equal to or very close to? Now I want you to make a correction here. I lost, excuse me, a square root. It should be sigma over the square root of n. All right, so if you please pause and make sure you absolutely get that correction. So we're going to take the values that we had and from last time's notes, and our sample size was 5, and that ends up being 0.947. So yeah, those are pretty close. Yeah, they're close. Why does it make sense, though, that the shape of the distribution of sample means is not bell-shaped? So it seems like, well, wait a minute, we've done some stuff from the central limit theorem, we did some calculations, and the numbers are pretty close. Here's the thing. The overall shape of the distribution is approximately symmetric if the population comes from a normal distribution, which we saw just a few minutes ago when I went back to the previous notes. It absolutely is not. And the sample size is large enough, which is typically 20. What was our sample size here? It was only 5. So because the sample size is not large enough and is only 5, which is definitely less than 20, nor is the population distribution normal, therefore it's not going to look like, based on the central limit theorem as we go back up, it's not going to look normal. It's not going to be bell-shaped. It says bell-shaped or is approximately symmetric. It's not going to be symmetric, not bell-shaped, or you could say symmetric. All right. Suppose now that we've taken samples of 20 words instead of the 5 words that we took. How, if at all, would the following be different for the distributions of sample means with samples of 20 words versus 5 words? That's interesting to think about. If we think about what we saw before, we looked up here and we saw when we just had 5 that the mean was pretty close. Do you think the mean is going to change a lot? Probably not. It's going to stay about the same. It's going to stay pretty close to what it was because it was already pretty close to the population mean. The standard deviation. So now we have more words. Remember when we're finding the standard deviation up here, let's go back up here. We're going to take and divide by the square root of n. So if we divide by a bigger number, what happens? Take a minute, and if you take, let's say, 2 divided by 3, you get 2/3. If you take 2 divided by 20, you get 1/10. So what's going to happen to the variability? Is it going to increase or decrease? It's going to decrease. So it was about 0.948 before. It's going to decrease quite a bit as your sample size goes up. And you can calculate that to check, but it makes sense because remember you're dividing by the square root of n, so you can check that. the shape will become more or less or stay the same, symmetric and bell-shaped. Remember, we needed at least 20, right? Now we have 20. I'm going to say it's going to become more symmetric and bell-shaped because we're going to have more observations. We'll have more in our samples, and when we take those means, so it should look better. So applying what you know, suppose that you take a sample of 10 words and the average length turns out to be 5. Is there evidence that this sample had unusually long words, or is it fairly typical? Now, what you want to do is use what we know from above and apply that and give that a shot, and then come and check your answer. So pause the recording for a moment, please. So looking at number 5, remember suppose that we took a sample of 10 words. Hopefully you did the calculation out. We're going to use that population mean of 4.295, the standard deviation of 2.119. We're going to remember a change, adjust based on our sample size, which is 10. So we divide it by the square root of 10. And you notice it's 0.67. Does that make sense? Yes, remember we said there's going to be less variance. Originally it was when we had that a smaller sample size, we had a larger standard deviation. So as our sample size goes up, our variability within the sample will go down overall. So the variability went down. That makes sense. The standard deviation went down. I calculated, so it says, is there evidence that this sample had unusually long words, or is it fairly typical? The average length was 5. Well, given I have a lot of information already, I'm going to use that z-score. So I took my 5 minus the mean and divided by that adjusted standard deviation and came out with 1.05. Now, is that very far at all from the if we look back at our chart? No, that's not a very large z-score. So with a standardized statistic of 1.05, we don't have much evidence that the sample had unusually long words. Number 6, but does the size of the population have any impact on the distribution of sample means? I want you to explore that by increasing the population times by 4 and then by 40 times in the applet to see whether anything about the distribution of sample means when we say sample size is 20 changes. So pause and give that a shot. What you're going to find is there's no impact of population size. Now, the same sample size matters because that affects the standard deviation. So we're assuming that as we're doing this, we're not changing the sample size, we're just changing the population size. But sample size obviously affects the standard deviation, as we've seen. So the population size doesn't have any effects, everything else being equal. So far we've talked about the central limit theorem with means, but let's look at it again with proportions. We're going to revisit that to help us figure out something about the central limit theorem. It's very similar, but with proportions. Once again, we have the 268 words in the Gettysburg Address be the population of interest. Suppose we want to characterize this passage by reporting the proportion of E words. Once again, I'm just taking what we had from before to explore the long run pattern of p-hat. We're going to use the applets again. I used it, and I'm not going to go through this. Oops, sorry, I just hit my screen there. My finger all the way through. You can go through this now. So you want to go back to that sampling words, make sure Gettysburg is selected, and then select the variable has seen. It's on the right-hand side below Gettysburg. And I took a screenshot. So this is based on the population. All right, so this is every single word. Remember, we're using this. It's a little unusual to be have the population, because usually we do sampling to find out something about the population. We're using the Gettysburg Address with known population parameter or that we know all the values of the various parameters, because we want to compare to see how the sampling works and if it works or not. So the proportion of does the words have E in it is yes, is 0.466, and the population size is 268. Is that a statistic or a parameter? And at this point, hopefully that's quick and easy. It's a parameter, and we know that pi, because we're looking at specifically proportions. We see proportions, and that's 0.466. Now, I'm going to pause the video for a minute and just rewrite the words that I had last time. You can write your words or use mine. So we want to take the one random sample. Instead of using that random.org, we're going to use the applets, and once again, click on show sampling options. And I used, like I said, the sample before, and now, though, instead, we just want to know if a word has at least one E. And I can see right away, now, no, power, yes, 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 yes. So the applet displays a proportion of words with E in the most recent sample of 5 words. So if I had done that, obviously we see 4 out of the 5, which comes out to be 0.8. So I can put that right up there. So you can repeat this many times, like we did before. I'd like you to try it. I went through it with the when we were looking at average length of words. Here, why don't you try with the E's? And hopefully by the end, we're going to use, for the rest of this, I'm going to use my proportion that I'm using proportion and the sample proportions that I came out with my sample distribution. How many dots are there? And I hope at this point, this is like a no-brainer, 1,000. What does each dot represent? So each dot represents, hopefully this is once again pretty straightforward, each dot represents the proportion of words with one or more E's in a sample of the 5 words. So obviously it's going to vary depending, and if you do this, will your distribution here look a little bit different? Definitely. Should it be fairly similar? Yes. If it's not, there's probably a mistake in there. What's the shape of the distribution? Can I say it's pretty bell-shaped, or is it slightly skewed? Well, first of all, there are lots of gaps, right? We see lots of gaps here. So it's not pretty and smooth. We see gaps all throughout here. And we also see that it's getting pulled up a bit by over here. So whatever's pulling it up is what side it's skewed to. So looking at this, would you say right or left skewed? I'm going to say it's right skewed, because there's more over here that's pulling that average up, or that mean up. So right skewed. The mean and standard deviation for this graph, it is reported to you right here. So the mean is 0.456, and the standard deviation is 0.225. As with means, it turns out the overall shape, mean, and standard deviation, yes, of the distribution of p-hats can be predicted. Once again, there's this very valuable theorem. Do you have to have these theorems memorized? Absolutely not. You need to know when to use them and whether it's appropriate to use them. So when we have random samples of size n taken from a large population, the distribution of values of sample proportion p-hat calculated for the samples has a mean of pi and a standard deviation of pi times 1 minus pi divided by n, take the square root of that, where pi is the population proportion of successes. Are we always going to know that? In this case, we do. We know the actual value. But remember, a lot of times we'll assign pi a value, right? 50-50, so it's 0.5. Also, the central limit theorem predicts the overall shape of the distribution is approximately symmetric and bell-shaped, in other words, normal, if the number of successes and number of failures are both at least 10, that is n times pi, is greater than or equal to 20, and n times 1 minus pi is greater than or equal to 20. So if you have, let's say, 20, and your pi, your that population proportion is 0.5, 20 times 0.5, that would give you 10, so you'd have at least 10. So you can, you have a nice way to check right here, and they need to be at least both 10, okay? The population is considered large if its size is at least 10 to 20 times the sample size. Do you need to show that or prove that most of the time? No. The one time you will need to make sure you're very aware of that is when you're looking at a problem, you need to look and see, is the population size large enough compared to the sample size? And vice versa. So you want to make sure that if you're going to use this, that you meet these criteria. So now we're going to verify the mean and standard deviation of the distribution of p-hats from the applet output with the formula suggested. So now we're just going to do what we did before. We're going to do some comparisons. So I suggest you take a moment, pause the video, and try this yourself. So I recorded it by applet and by what the central limit theorem would tell us. So the mean from the applet was 0.456. You can go back and look at that on the graph. And the standard deviation was 0.225. The central limit theorem, on the other hand, gives us a mean of 0.466, and the standard deviation, we took the pi times 1 minus the pi and took the square root of that. I got 0.223. Those are pretty close. They're close. Those numbers are not that far apart. Now, explain why the shape of the p-hat distribution should not be described as normal. There's lots of gaps in that graph. If you look back at the graph, there's lots of gaps. Lots of graphs. How about lots of gaps in the graph? And n equals 5. Nowhere near 10 successes and 10 failures. So how will the distribution of p-hat change if we take samples of 10 words instead of 5? How, if at all, will the shape, mean, and standard deviation of the distribution of sample proportions change? Now that's going to be very similar to what we did before. The shape, as the sample size goes up, it should become more symmetric, look more normal. The mean is going to stay about the same. So remember, they were already pretty close, and as we get more and more observations, we're going to get closer and closer to that population average. And as the sample size goes up, remember sample size is n, variability, remember measure of variability is standard deviation in the sample, goes down. All right, because remember this number here, we divide by n. Remember, as we divide by bigger and bigger numbers, whenever you divide by a bigger number, you're going to end up with a smaller number overall. What if we do it with samples of 20 words? What do you think? These two, I would say, are good. What about the sample of 20 words and the shape? Based on that theorem, and based on what we've seen so far, the shape is going to get more symmetric and it's going to be more filled in. Once again, if you want to recalculate the standard deviations to see what happens, you can always do that to check yourself. But remember, sample size increases, the variability in sample means is going to get smaller. So take a moment applying what you know. Let's see, you have a fair coin, it's tossed 20 times, and it lands on its head on heads 17 times. How unusual is this, if at all? Explain using the appropriate calculations, and how are you deciding? So this is kind of pulling together what we've done so far, and I'm going to pause this right at the answer and then show it to you, and that's the end of week 2. One last bit, remember Once again, as the sample size increases, the variability in sample means gets smaller, okay? So if you're struggling with this still, make sure you run through the calculations a couple times using the formulas. Have a good day.